Good morning or good afternoon, ladies and gentlemen. Today, I would like to talk about some of the advances in lithium-ion battery that we carried out at Argonne National Lab and our collaborators and beyond. Initially, I was going to focus on different technology within the beyond lithium-ion, but because of the time limit, I will focus only on sulfur system. Hopefully, in the future, I can talk about lithium air and some new system we developed based on lithium superoxide. Let me start with this very busy slide that basically represents the global human activity energy flow, where it says that beside transportation, all the other application, either residential, commercial, or industrial, rely on many sources of energy that span from renewable energy, nuclear, coal, natural gas, and oil. The only application, which is transportation, rely on one source, which is oil. But the story doesn't end up here because half of the energy is wasted in heat. So not only we are relying on one source, but we waste half of it. So the situation is very unsustainable when the demand increases. Now, in the United States, mobility is a large part of the US energy economy. About 70% of petroleum used are for transportation. And within that 70%, 85% is used for on-road vehicle. In US also, transportation is the second largest expense after housing. So you can imagine if we develop technology to expand mass electrification, it will impact significantly the US energy economy, not only US, but also China, Japan, and Europe, and other countries. Now, the good news is that the electrification is underway. There are regulatory requirements set by a number of countries led by Europe. For instance, in Europe, they actually mandate 58 miles per gallon by 2020. So I assume it's already there. China has 56 miles per gallon. With this, basically is an average between conventional vehicles and electric vehicles. United States is 54.5 miles by 2025. So if you look at the global EV forecast by Bloomberg News Energy Finance, you can see that the growth will be exponential. By 2030, we expect at least 25 million electric vehicles produced each year or more. Now, at 2020, you can see that the number is very low, is about 2.5. It's actually very conservative because I heard that last year China has basically built more than 2 million electric vehicles alone. So these numbers are very conservative. So I expect those numbers will be much higher going forward. And they are basically driven by China, US, and Europe. Now, the reason why the numbers are very small now is because there are still some barriers that need to be addressed. And one of the key barriers is the cost. So current projected cost is 2 times higher. So DOE near-term target is $110 to $120 per kilowatt hour. And in the long term, by 2030, for instance, we need to be at $80 per kilowatt hour. If you are at this number, then we achieve parity costs between conventional vehicles and electric vehicles. So basically, will be the beginning of the end of conventional vehicles. Now, to reduce the cost, the only way to do that is to increase the energy density of the system. We need to be at least 350 watt-hour per kg, comparing to 260 now or 270 watt-hour per kg that is used in electric vehicle at the moment. Now, let me explain why increasing the energy is very important. If you take, for example, a conventional Generation 1 Nissan Leaf pack, it's a 23 kilowatt hour, 500 pounds, and 125 liter. Imagine if you increase the capacity of the chemistry inside the battery, you can still get that 23 kilowatt hour, but the weight and volume drop significantly. So now we are reducing the cost across the board because not only are reducing active material like cathode and anode, but also inactive materials like separator, current collector, electrolyte, and so on. So because of that, now the cost drops significantly. Now, how can we increase the energy? We can do that by increasing the capacity of the cathode. As you know, lithium-ion has a cathode, anode, and electrolyte. We have an opportunity of increasing the cathode capacity by 80%. We can also do it, and this is the simplest way, by increasing the stability of the electrolyte to high voltage. Some of the conventional cathode that exist at the moment, they can achieve 280, 300 watt-hour milliampere per gram, but they decompose because, or they react aggressively with the electrolyte because of the instability of the electrolyte. The last one, which is also very significant, is to shift from graphite, which is used as the anode of choice at the moment, to a different anode like metal oxide, or intermetallic composite that can offer an opportunity of 300% or 3 times practical capacity increase. So I will basically show you an example of how can we improve the cathode capacity and stability. One example on the electrolyte and one example on silicon. Some of those the technology that I'm present are under validation for EV, or some of them has been licensed and being used in electric vehicle. Let's start with the cathode. Now, if you take, for example, the lithium nickel cobalt aluminum oxide, that's the NCA, is very popular. Tesla pioneered this material for their batteries. If you operate at 4.2 volt or 4.3 volt, you can get some very good cycle life out of the system. However, if you go higher in voltage, 4.5, 4.6, you get very high capacity, up to 240, but the cyclability dropped very quickly. So the material doesn't cycle well. So at Argonne, what we did, we taken particles from electrode at the end of the life, and then we microtone them in half and look at them by high resolution electron microscopy. And this is what you get. You get the layered structure, as you can see. But then you have another phase through electron diffraction is actually a nickel oxide phase, which is very, very resistive, not permeable to lithium if you want. And we have a surface film as well. So what happened is that when you remove lithium from this nickel-rich, nickel 4+ in an oxide phase, thermodynamically is unstable. So you have an immediate reduction, you form nickel oxide. That's the phase we've seen here by electron diffraction. And then you have oxygen release that react with the electrolyte and form this surface film. So the consequence of this phenomena is a significant increase in the interfacial impedance of the cell, and that causes failure or capacity fade that we've seen. Now, what the industry has been doing so far is to do coating to prevent this type of reaction. So this is the typical coating that the industry is using. For example, I think there is one missing, but it's okay. So basically, this is what happened. When you do a coating, you basically disperse nanoparticulate of metal oxide or metal fluoride on the surface of the material to form not exactly film, but it's just nanoparticulate deposit on the surface. So you don't cover the whole surface, but those can actually impact the stability. Again, you can at 4.3 volt, you can get better stability, but at high voltage, basically, you have some additional phenomena. One of them is the cracking, as you can see. Another one is the release of oxygen that cause reconstruction phases or phase transition at the surface from a layer to spinel. So these things are very difficult to overcome when you operate at high voltage. So what you need really is a very uniform conformal coating that cover the whole particle inside and outside. And you cannot do that by a simple co-precipitation of metal oxide on the surface of the active material or the secondary particle of the active material. It's almost impossible. So what we did at Argonne, we developed here is it. You can see that clearly. When you do the coating, you get this type of particulate. At low voltage, you can get some performance enhancement, but at high voltage, you still have significant cracking, as you can see here. So this cannot be overcome when you go higher in voltage. So as I say, at Argonne, we developed a very unique coating technology. It's based on a gas phase polymerization to form a polymer, a p-dot polymer that is both conductive ionically and electronically. So you get some ionic conductivity to allow for lithium to move in and out of the grain boundaries or inside the particles, and you have conductivity to enhance the overall conductivity of the material. So we take an E-dot, which is a gas, and vanadium oxychloride, an initiator, which is also a gas. Gas go everywhere. It penetrates the particles, and then you heat it up at 100 degrees C in a rotary reactor, and you form a polymer, p-dot polymer, that basically create a uniform coating across the particle inside and outside. This is the conductivity of the P dot. This is our work, and you can see it's highly conductive electronically. The P dot structure is shown here is ionically permeable by hopping from one oxygen to another, similar to the PU concept. We also find out that the P dot is a HF scavenger. This is important because the salt in the electrolyte is LiPF6 that can hydrolyze and form HF, and HF can actually dissolve some of the transition metal oxide from the cathode, leading to capacity fade. So by scavenging the HF, we can actually prevent this type of phenomena from happening. So the first thing we need to do is to confirm that we have a P dot coating. So what we did, we confirmed that by 3 techniques: FTIR, Raman, and XPS, which XPS, as you know, is a surface technique. Yeah, what we want to do is to probe, for example, the main component of the P dot, which is sulfur, as you can see here. So you can see clearly that when you start coating, depending on the time, you can form, there are sulfur peaks that are formed that does not exist in the initial bared material. We also compare the signature of Raman of the P dot versus the coated material. You can see they are the same things with the FTIR. So 3 techniques prove without doubt that we have a coating at the surface of the material. The next is we want to optimize the thickness of the coating, and we find out that the thickness is proportional to the coating to the coating time. For example, these are different time of coating, basically exposing the mix to 100 degrees C at the reactor. And we can see clearly that in all cases, we form very conformal coating. The best performance we got is at 60 minutes. We get 20 nanometer coating that is very uniform. This is outside the particle. Now, how about inside? We want to have evidence that we also have protection inside the particle, the primary particle we call in the grain boundaries. So we did a cross section of a particle and run it by TM and look at EDX to look for signature of sulfur. Sulfur is green here. You can see we have uniform coating at the surface of the particle, but then also inside the particle, there is tremendous amount of green, that's sulfur. These are polymer P dot that is inside the particle and also in the grain boundary. So we have clear evidence that we basically protect the whole particle. So the impact of this protection is a significant improvement in cycle life. This is a nickel-rich. When you have nickel-rich, the reactivity is high. So when you operate at high voltage and high temperature, you can see the capacity fade without protection. With protection, you get much better stability. At high voltage, 4.6 volt, we get about 250 milliampere per gram, sorry. And you can see clearly that the protected material shows very sustainable cyclability, while the non-protected material goes down very quickly. So again, as I said, the biggest concern is cracking and oxygen release because it can affect the safety of the cell. So we looked at that as well. So here is a material that has been cycled for 100 cycle at 4.6 volt. And then, as you can see, there is tremendous cracking when you don't have a protection. Once you get a P dot coating protection, we don't see any cracking at all, which means we don't have any phase transition that caused this strain from a layer to spinel that caused this strain that created this cracking. We confirmed that by high resolution X-ray at the advanced photon source. When we charge at high voltage, you can see spinel phases are formed without P dot coating. However, with the coating or the protection, we don't see any phases forming, and therefore we don't have any oxygen release. We did confirm that by mass spectrometry. You can see that all the way to 500 degrees C, we did not see any oxygen release that creates spinel phases and rock salt, while with the bared material, at about 250, you have an oxygen release that is caused by, that created a transformation from layer to spinel. And then when you go higher in temperature, you have even more oxygen release that basically lead to the spinel to rock salt transition. So you know that when you have oxygen release, it will react exothermically with the electrolyte and create significant thermal hazard. As you can see, when we add electrolyte to the charged electrode cathode, you can see we have a reaction that is very significant that happened at very early temperature. While with protected material, we did not see any exothermic reaction. We have an endothermic reaction or electrolyte depletion, if you want, because of evaporation. Now, if we just take the electrode without electrolyte and charge them to 4.6 and heat them up, you can see the material without protection decompose and generate some heat, while with the coated material, did not see any decomposition. So these are indication that this unique coating not only improve the cyclability, but also improve the safety of the material. So this is one way of doing a protection to get at high voltage and get very high capacity and good safety. Another way is a totally different design of at the particle level. We call it developing a full concentration gradient across each particle. So we know that nickel rich cause reactivity. I've shown you the data, the interfacial resistance goes up. So what we did here, we developed a process where we can bury the nickel in the bulk and slowly reduce the nickel and increase the manganese to get stability at the surface, so we can operate at high voltage. Manganese is very stable. This is a PMA that shows that the nickel is going down, the manganese is going up. We keep the cobalt constant. The first question is this material scalable? The answer is yes. We use a co-precipitation. The conventional NMC that is used in electric vehicle use only one tank that has a defined concentration of nickel, manganese, cobalt, and you send it to the reactor, and you have a chelating agent and co-precipitating agent, and you form your material. Here we have two tanks, one that is nickel rich, the other one is manganese rich. We start sending nickel to form a nickel rich bulk, and then we delete the nickel tank with manganese, and we slowly change the concentration by growing the particle. This is the morphology of the material. It's very different from the NMC conventional material. It's also spherical, but inside we don't have like round edge primary particle, we have rods. And then if you look at the EDX, you can see that the red is nickel. And then when you start getting to the surface, it becomes green, that's manganese. You can see it also here. It's green, and this is the opposite now. The green is nickel here. It become orange because the concentration of manganese increase and the nickel drop. And then when you get into the surface, you have mostly manganese. So have a very good layer protection because of the manganese existing at the surface. So what we did a comparative study where we taken a coated NMC that is used in automotive of today, and then we make a average composition similar, FCG we call 622, but keep in mind that the nickel is 100% in the bulk and is lower in the surface. So the first thing we find is the density of the material is much higher than the commercial material used for electric vehicle. Density is very important because you can pack more active material in the electrode, and that can lead to more energy increase. The reason why the density is higher because of the primary particle are raw and very dense. We also looked at the concentration gradient within the primary particle. They also change, as you can see from the cobalt nickel ratio is changing. Now, the most important observation is that when we did an TM, we noticed that the layer structure of the material is parallel to the rod, which means lithium can move very fast without going through the grain boundaries. And that can allow us to pull most of the lithium at a defined voltage. What I mean is, for example, if you take these two materials, charge them at the same voltage, let's say 4.3 volt, you would draw more capacity out of the material because of the ease of moving lithium out because of this unique configuration. And we were right. This is a charge-discharge curve of both commercial and FCG. You can see when we operate at the same condition at 4.3 volt, we had about 180 for the conventional. We had about 225 for the FCG because of that unique, morphology that I just showed you. We did some pouch cell tests, different pouch cell, to prove that the FCG material outperformed the conventional material. You can see at high voltage. In this case, is the cathode is at 4.4 volt. The cell is at 4.3 volt. Now, the problem with the nickel manganese cobalt is as long as you have some HF, you will get some dissolution, and the impact of dissolution, especially if you operate at high temperature, like 55 degrees C, the capacity goes down because you have dissolution, as I mentioned, and these metals basically move to the anode side and basically react to compromise the SCI of the anode. And as a result, you see, the interfacial impedance of the anode increase. So if we really want to do a validation in a real industrial cell, we have to figure out a way to put a different passivation film that is very robust to the attack by these metals. And that's exactly what we did. We developed a tetrafluoroxalate phosphate additive, small amount, less than 1%, you put it in the electrolyte, it polymerizes and form very stable, uniform film at the surface of the anode. This is DFT calculation that give us the how the polymer is formed. And then when we test it versus carbon at high temperature, you can see with the conventional SCI, the capacity goes down, while with the new SCI that we form, we have very stable material for almost 100 days of aging, so very robust. So we use this additive in collaboration with our industrial partner that scale up this material, and we use an aggressive composition, which is FCG 811 versus NMC 811. So the industry, by the way, are trying to enable this material in the next generation electric vehicle, because this material provide very high capacity versus NMC 622. So these are the initial data at 4.3 volt with the additive. You can see that this is actually not so bad as a result for developed under development NMC that the industry is trying to enable. It gives us about almost 80% retention after 300 cycle. However, the FCG shows far much better result with almost 550 with 10% fade only. Even at high temperature, the FCG outperform the NMC 811 at room temperature. So this is a technology that's been licensed by Microvast, and they have scaled up this material, and they were able to achieve almost 280 or 290 watt-hour per kg with this technology, and is being actually produced for use in electric vehicle. In this case, it's 270 watt-hour per kg. So you can see clearly they pass all the safety tests. This is a very large cell. They pass the overcharge. They have actually better performance than us when they put it in a full cell, because they are much more expert in building electrodes and all that also. So actually the expectation is they will get 3,000 cycle at room temperature. Now the recommendation for electric vehicle cycle life is only 1,000. Even at high temperature, they can achieve 2,000 cycles. So this is very, very impressive result. Now, the reason why this material is safe is because the cathode is safe. You can see when we charge the cathode, comparing to the NMC 811, for instance, you can see that the NMC 811 has an early reaction and the overall heat is very significant. However, the FCG has much resistance to reactivity. You have to heat up at higher temperature. The activation energy is very high, and the overall heat is very small. So it generates very small heat, even though at high temperature. So that's one thing. The other thing is the additive we put in is also play a big role. This is a DSC of the anode. So normally in conventional SCI decompose at 100 degrees C, and you start forming a significant heat because of formation and decomposition of the SCI. So this reaction can accelerate the reactivity of the cathode. However, if you use these stable additives, you can see you have to go much higher in temperature to decompose it. So you basically save all this energy and prevent an early reaction with the early reaction of the cathode. So that's basically on the cathode side. On the electrolyte, as you know, if you operate at high voltages using, let's see, conventional electrolyte like EC, EMC, when you start operating at high voltage, you can see the capacity drop almost to zero, and the efficiency drops significantly. If you take, for example, this high voltage cathode, the graphite, and do a floating test at different voltage, you can see that the leakage current is going up, which means you have decomposition is happening. At Argonne, we have looked at fluorinated solvent. This is a mistake here, sorry. As a potential electrolyte for high voltage. You can see we looked at a whole bunch of different fluorinated solvent, either fluoro-EC or fluoroalkali EC, or fluorinated linear carbonate and ethers. We looked at also sulfones and fluorinated linear sulfones. So, and a combination. The first thing we did is we applied the DFT calculation to look at the potential of stability of this electrolyte. You can see in most of the case, they are operating at much higher voltage than conventional electrolyte, in a 7, 6, but this is as a solvent itself. So when you put this solvent in the presence of highly oxidative cathode, this number will drop, but they're still higher than the conventional electrolyte. We have looked at different composition. You can see fully fluorinated has 210-3, which is very robust for electric vehicle. is high conductivity. We did a floating test. As you can see here, we don't see any leakage current until 5.2 volt. And we taken this chemistry, which is high voltage, is 4.8 volt, and run it at high temperature. You can see without with the conventional electrolyte, the capacity dropped to 0 after 400 cycle. With this new electrolyte, we sustained significant capacity retention at these high cycle ability. We also look at the flammability of this material using a flame test. For instance, we take a glass wicks, fill it with the electrolyte, and hit it with the burner and see what happens. So we start first with the fluorinated electrolyte. As you can see, once you hit it with the flame, it doesn't catch flame, as you can see here. However, if you do the same things with the conventional electrolyte in the next, so if you do, for example, the ECDC in LiPF6, you can see clearly that the electrolyte will catch flame until you basically burn all the electrolytes. So that's a bonus. The third concept is basically anode. There is an opportunity here. So far, the graphite is the main anode, which is an intercalation concept. If you move to metal, you basically move to a conversion reaction. In this case, you have a whole bunch of metal to select from. Obviously, silicon is very attractive because it's dirt cheap, and it shows the highest volumetric and gravimetric energy density than any other metals. You compare it to carbon, is almost 10 times theoretically. Obviously, you cannot use 10 times because there is no way you can design an electrode that is very thick to absorb all that lithium from the silicon, from the cathode to the silicon. Now, the problem with silicon is that when you operate, when you alloy almost 4.4 lithium, you have a significant expansion in volume. And this expansion can cause a major problem. This is an area where we did an AFM, where we have a fresh electrode as a comparison and a scanned electrode. So once you start alloying lithium with silicon, you pay attention to this right figure here. Hopefully it's very clear. You will see that the cracking start happening, and the crack become very significant once you go to higher charge. See that? So this is initial, the first cycle. So the problem is that you create cracking, and at the end, you have a pulverization of the particle and isolation, and then you have a significant capacity fade. So we need to address this. And a tremendous amount of work has been done on trying to incorporate silicon inside different carbon matrix, as you can see here, or basically designing conductive binders that can incorporate the silicon when it pulverized, for instance. And they've shown some decent result. The only concern here is that the loading is very small. So you have a shallow charge and discharge. At Argonne, we developed a new technique where we use a gas, because gas can go everywhere. Again, so to incorporate the silicon in graphene, dissolve the graphene that is basically exfoliated using acid. The advantage here, we use hydrochlorosilane, is very low cost material that is used for the silicon wafer. It's about $8 a liter. The idea is to basically reduce this one once it goes inside the graphene sheet and form silicon like this. The amount of the morphology of the silicon is spherical, but very small. It's less than 150 nanometers, so it takes a long time to crack to start with. And if there is cracking, this graphene layer will collapse on this this sheet of graphene will collapse on the cracked material and keep conductivity. And you can see clearly the impact here is very significant. We're also seeing some improvement in efficiency, but we still have a very large irreversible loss that need to be addressed. Now, if you reduce the silicon amount, you can get actually lower capacity, but still higher than graphite, but you can operate at high rate and get very significant cycle life out of this system. So the idea here is the hydrochlorosilane, when it's used in a silicon wafer, it gets contaminated. You use that contaminated material that are not reused as a source for lithiating the as source of making silicon graphene anode material. So this is the reactors that are full of this gas in one of these companies, and then basically that's how you do it. So it's taking advantage of a byproduct if you want. So the cost will be very significantly lower. Now, again, the biggest problem with the silicon is the large irreversible loss. Notice here, for example, the difference between the charge and discharge is almost 150 or 180 milliamp hour per gram. That's basically the capacity of the cathode. Now, if you have a small amount of irreversible loss, like in graphite, you can use excess of cathode, as you can see here. But if you have large amount of irreversible loss, then it's difficult to use a lot of excess of cathode, because cathode is expensive and heavy, so it defeats the purpose. So you cannot do that. You have to come up with a pre-lithiation technology, and that's exactly what we've done. So we used, for example, lithium or lithium peroxide, because this material has very high capacity. We can use 1 or 2% on the cathode and activate it and send the lithium to the anode. Very simple process. The question is how you can activate this material. Are they compatible? Are they stable in the presence of this cathode, and so on? So here is an example. When you add 1% of lithium, you can see that the charge capacity increased significantly, almost 600. It's supposed to be 300. It's by another, I think in this case it was more than 1%. That's 5%, sorry. And then the other things we did, we taken a bad anode, and then we cycle it, initially charge and discharge. The cathode, so this is supposed to give us 254 milliamp hour. We get only 176 because a lot of lithium is lost because of the cathode. Lithium from the cathode has to compensate for the irreversible loss of the silicon. However, once we add the lithium, you can see we can recover the whole capacity. So this is an approach. Unfortunately, this is an industrial work. We are working with a company, a vehicle company in Europe, that we are actually in the process of enabling this technology. So I cannot talk too much, I cannot show data, but believe me, this is a very nice approach where we can completely activate all the lithium or lithium peroxide and basically improve, compensate for all the irreversible loss from silicon and improve the cyclability as well. Now, if you use the techno economy model that Argonne developed and is available online for everybody to use, if we use the NMC graphite, we are at about 220. This is the cost, and it's distribution of the cost. If we move to the silicon, without pre-lithiation, we are at 125. So we are in the near term, if you want. So if you add the pre-lithiation, we drop to 100. But however, if you do sulfur, you can see clearly that the cost drops significantly. And that's the reason why I would like to talk about sulfur in my last part. Here is the sulfur. It's a 2-electron transfer. It has an average voltage of 2 volt, many multiple steps because of dissolution of polysulfide. As you can see from here, the overall gravimetric energy is very high, 2,500 watt-hour per kg. It is very abundant, environmentally benign, and the cost is basically dirt cheap. 1 ton of sulfur is about $110. Practically, you can double your capacity if you use it in a full cell versus existing lithium ion, as you can see here. So this is very attractive, and the sulfur is a byproduct of petroleum industry. So there is a lot of mountains of sulfur sitting everywhere. But it does have a lot of problems. The first problem is actually conductivity. Sulfur is insulating. So obviously you need conductivity to allow for electron to move in and out. And so the majority of the scientists has been mostly focusing on incorporating sulfur on carbon. The good news is sulfur can melt at about 100 degrees C, so it's easy to melt it and incorporate it in a porous matrix, carbon matrix. The second one is actually low mass loading, because it's expansion when you react to lithium with sulfur, you form Li2S, and then you have an 80% extension that you really have to accommodate on when you design your cell. The most difficult problems are basically the shuttle effect or the dissolution of polysulfide that lead to loss of active material. This one has not been fixed completely. And The other one is lithium metal use, which can lead to dendrite and reactivity. It's the holy grail of all the problems. So these are the two things that need to be focused on to enable this system. So I'm going to talk about mostly how we enable the shuttle effect. Now, instead of using carbon, in most cases, with 10, 20, 30% carbon, that can actually impact the capacity because you are using a lot of inactive material to address the conductivity of sulfur. We actually use selenium. Selenium is active also. It has half the gravimetric capacity of sulfur, but it has almost the same volumetric capacity because the density of selenium is twice that of sulfur. But the biggest difference is selenium is 20 order of magnitude higher conductivity than sulfur. So if you put them, if you look at the phase diagram, there is a whole bunch of phases. Once you start adding selenium, the conductivity of the material goes up. So we thought maybe that's the best approach to address the conductivity. These are the phase diagram. You can see, of course, selenium is expensive. It's about $80 a kilogram. It's almost, you can buy a ton of sulfur with that. But if you can get the lowest amount of selenium, like selenium 22.2 SC, then the cost goes double, basically, from 110 to 220 a ton, which is extremely low cost. These are not mechanical mix. These are real phases that are forming. This is a Raman spectra of different phases that are totally different. So at Argonne, we developed a fluorinated electrolyte. We call it HFE, and use this material and see what happened. And you can see with the sulfur with the ether base or like DME, for instance, you have multi-steps that are indication of the polysulfide, the dissolution. With the new electrolyte, we have one step. We have one reduction peak that tell you that you move from sulfur to Li2S without this phase dissolving. We also look at the electrolyte color. You know, if you have an ether base, you have discoloration. That is a sign of dissolution. We don't have it, but coloration is not really a scientific way to make that judgment that there is no dissolution. So we developed a new technique at Argonne using the advanced photon source, using the XAPS, X-ray absorption spectroscopy. XANIS is a good technique because it can probe the oxidation state of materials either in the amorphous phase or crystalline phase or in a liquid phase, and so on. So at the APS, you can basically run one spectra within 1 minute. And then, so you basically can discharge your cell and run thousands of spectra to look at any shift due to the change in the oxidation state in the solution. And that's exactly what done. So once we did that, this is actually many spectra during the charge and discharge. If you have a dissolution, you get a reduction of the polysulfide, of the sulfur, and therefore you should see a shift toward lower energy. You can see we don't see that shift. We have a flat curve, which is an indication that we don't have any dissolution at all. We also did a DQDV that shows that we have one reduction peak comparing to multi-step reduction due to the polysulfide dissolution. My colleague Curtis, Larry Curtis, this is a DFT calculation for the solvation energy. He calculated those solvation to see in ether base and in HFE. You can see with the NL1, which is the HFE, the activation energy is very high, difficult to solvate. So they don't dissolve basically. And we did a performance test using 70% of the selenium sulfur. In this case, we operate at 1C and 2C. You can see the performance is actually very good, good cyclability at this very high rate. This is without optimization of the electrode. So there is a tremendous opportunity here. So my conclusion to you is electrification of vehicle is underway with low growth, need to reduce cost, obviously. And if we do that, then there is an opportunity with massive commercialization of electric vehicle. I have shown you a few examples of developing the next generation lithium ion to get us to that 350 watt-hour per kg or higher. And then this new system, which is still low cost, selenium sulfur with new electrolyte, at least we overcome the conductivity and the dissolution and the Shadley effect that are one of the main barriers to enabling this system. So I would like to end by, of course, acknowledging all my coworkers at Argonne National Lab Also, my sponsors at DOE, Dave Howard and Tien Dian, which have been very generous sponsor for many, many years. And some of my international collaborators as well, like Go Chen from Hong Kong PolyU, and Oyan Mingo from Tsinghua University, and Fred Pan and from Peking University, and Minhua Shao from Hong Kong University of Science and Technology. And I would like to thank you all.